In this video, I will try to present the Father Himalaya objectives and the means he has imagined and built to achieve them. His real name was Manuel Antonio Gomes. He was born in 1868 in the north of Portugal into a poor peasant family. To enable him to study, his parents enrolled him in the seminary of Braga, where his colleagues gave him the nickname Himalaya because of his large height. He was a curious student, who was not always satisfied with the classical theories taught by his teachers. After the seminary, he became a teacher at the colleges of Formiga, then Coimbra, where he was a director, and finally Porto, where he was a chaplain. Starting in 1897, he started designing and manufacturing solar concentrators. His goal was to improve the yield of agricultural land with low-cost nitrogen fertilizers that he would like to obtain by oxidizing atmospheric nitrogen. This chemical reaction requires a large amount of energy and occurs in nature when lightning strikes occur during thunderstorms. The Englishman Crookes had reproduced it with an electric arc. Father Himalaya thought that for industrial production it would be more economical to use concentrated solar radiation. In 1899, he decided to go to Paris and enroll at the Collège de France in order to improve his scientific knowledge and realize his project. At that time, the most efficient way to concentrate solar radiation was the parabolic dish. However, it has two drawbacks. For large mirrors, the focus is difficult to access. The focus is above the dish, so that the molten materials may fall on the mirror. We have a good example with the 3 meters diameter mirror built by Willy Kohn in the 1950s. The dish had to be turned upside down in order to install the samples to be treated in the focal area. At the end of the 19th century, industrial solar facilities were used to operate thermal engines. The mirrors, which could be cylindrical, parabolic or frustaconical, concentrated the solar radiation on a line where the receiver was placed. The engine was powered by steam emusho, or hot air Ericsson. Of course, the flux density in a linear focus was lower than that obtained on a point focus, and insufficient for the Father Himalaya project. Due to the drawbacks of classical parabolic mirrors, Father Himalaya was led to use other areas of the parabola to concentrate solar radiation in a point focus. He used successively parabolic rings above the focus. In this way, the focus was placed under the concentrator. Parabolic sectors located at the focus level. In this way, the focus was placed on the side of the concentrator. As a single parabolic ring intercepts only a relatively small annular surface, Father Himalaya had the idea of associating several parabolic rings with the same focus. These are homofocal parabolas. A first prototype with 3 rings was built in 1899. We have no images but only a drawing of this apparatus. It measured 2.5 meters in diameter, representing an aperture of 4 square meters. The tests took place at Neuilly from March to May 1900. Father Himalaya estimated the temperature reached at about 500 degrees Celsius because the apparatus was able to melt lead and zinc. This temperature was very insufficient. In a patent filed in 1899, Father Himalaya described an operational version with a large number of rings. For ease of manufacturing, these rings were frustaconical and not parabolic. They were arranged so that the focal area was a segment of about 10 centimeters in length. There are 2 notable features. This version has a controlled atmosphere enclosure for the nitrogen oxidation reaction. The mirrors are getting longer and longer when you go from the edge to the center, but these long mirrors were difficult to make. To avoid the introduction of excessively long mirrors, Father Himalaya designed a parabolic elliptic concentrating device in the shape of a diabolo. The figure on the left shows that one segment of a parabola concentrates the incident radiation in its focus. This focus is also that of an ellipse, and the radiation from this focus is concentrated on the second focus of the ellipse. The long mirror is thus replaced by 2 much shorter mirrors. The examination of the optical paths on the right figure suggests that the ideal shape was also replaced by 1 or more frustaconical sections. This solar furnace, built in the Paris region, was assembled and tested in Ceride, in southern France, during the summer of 1900. It measured about 5 meters in diameter, included 14 frustaconical rings and 2 diabolos. The mirrors were made of bronze and the concentrator was oriented thanks to an azimuthal mount. A controlled atmosphere enclosure was designed to study the behavior of gases. This device allowed to melt aluminum but not bronze. Father Himalaya therefore estimated that the temperature reached was about 900 degrees Celsius, still insufficient to obtain nitrogen oxidation. This solar furnace had another drawback. The focus was low and easily accessible when the sun was high in the sky, but it was out of reach for an operator on the ground when the sun was low, that is to say at the beginning and end of the day. Father Himalaya found this defect prohibitive for an industrial application. He completely changed the shape of the concentrator so that the focus remains accessible throughout the day. This new concentrator was a parabola sector located 90 degrees from the axis at the focal spot. The aperture angle was 45 degrees. It was oriented so that the focus would form a horizontal circle when the sun moves. In this way, the focus was always at the same height from the ground and therefore easily accessible. This configuration, with a whole series of variants, was patented in 1901, with an addition to the patent in 1902. This solar furnace was built in Portugal and tested in Lisbon in 1902. With 80 square meters of bronze mirrors, the concentrator intercepted 60 square meters of solar radiation. On the day of the inauguration, in the presence of the king, the plumbago crucible melted. This failure did not stop Father Himalaya who, after repair, obtained very interesting results. He could melt several refractory materials such as iron oxide, silica, basalt, etc. but not lime, chalk or magnesia. The temperature was estimated at about 2000 degrees Celsius. Above all, the appearance of nitrous vapors was observed, indicating that atmospheric nitrogen had been oxidized. 2 years later, Father Himalaya presented a new model of solar furnace called Beheliopher. The concentrator had the same shape as the previous one, but there were two notable differences. The Beheliopher was equipped with a system of automatic tracking of the sun through an equatorial mount operated by a clock. This kind of device had already been proposed by Musho in 1878 and industrialized by Ennias in 1901 for solar engines. If the dimensions of the concentrator were the same as that of Lisbon, the mount was very different. The second difference was the replacement of the large bronze mirrors by more than 6,000 small glass mirrors of 123 by 98 mm. The focal area, located at an average distance of 10 meters from the concentrator, was only 15 centimeters in diameter. It thus received a very high flux density. The crucible was internally coated with magnesia to be able to withstand this flux. The Beheliopher was presented at the World's Fair of St. Louis, USA, which took place from April 30 to December 1, 1904. The construction and adjustment of 6,000 mirrors took 5 months. The tests did not begin until October but have yielded remarkable results. The melting of iron was achieved in less than a minute, that of refractory clay in 3 minutes, and even magnesia melted in 20 minutes. At the time, it was read that the temperature reached was 3,800 degrees Celsius, but today we know that magnesia melts at 2,850 degrees Celsius. The temperature reached must have been of the order of 3,000 degrees Celsius, which was considerable. For the Beheliopher, Father Himalaya won the grand prize of the exhibition, 2 gold medals and 1 silver medal. At the end of the exhibition, he was invited, with other exhibitors, to make a tour of the United States that lasted several months. On his return to St. Louis, the Beheliopher had been vandalized, the mirrors had disappeared as well as the clock, only the steel carcass remained. This destruction marked the end of Father Himalaya works in the field of solar concentration. He started manufacturing an agricultural explosive called Himalayite. To conclude this presentation, it will be emphasized that the primary objective of Father Himalaya between 1899 and 1904 was to obtain ultra-high temperatures by means of concentrated solar radiation. The proposed process should allow industrial production and be easy to use. In just 5 years, he has conceived and implemented several highly innovative concepts. His Beheliopher was, in 1904, the largest solar furnace in the world, the first to be oriented automatically.